In this video, we will continue practicing using the first derivative test to determine increasing and decreasing intervals and ultimately find relative maxima and minima. This problem has one additional element that I want to point out right at the beginning. Notice that f of x is undefined at x equals 0. For this reason, in addition to the critical values, we will have to use this number as well as we set up our intervals for the first derivative test. I mentioned critical values, so we need to find the first derivative in order to find the critical values. Before we take the derivative of this function, let's rewrite it a little bit. I don't feel like doing the quotient rule, which can be cumbersome, but we don't have to, because f of x is the same thing as I could do x to the fourth power over x squared plus 1 over x squared. All right, I'm splitting this apart. So this will be the same thing as x squared plus x to the negative 2 power. In this form, we can just do the power rule to find the first derivative. So f prime of x will equal 2x, and then we're going to have to use the power rule here, so the negative 2 will come to the front, and then we will have the negative 3 power. So f prime of x is going to equal 2x minus, and this part would be 2 over x to the third power. I really need to combine this all into one fraction, so let me think. We need a like denominator of x to the third power. So I'm going to have to multiply the numerator and the denominator by x to the third power so that I can make that happen. So in that case, I'm going to have f prime is equal to 2x to the fourth power minus 2 over x to the third power. Is this factorable? Well, f prime of x equals. We definitely have a GCF of 2 up here, so I can pull that out. So that will leave me with x to the fourth power minus 1 all over x to the third power. X to the fourth power minus 1 is the difference of two squares. So that's going to give me x squared plus 1 times x squared minus 1 all over x to the third power. X squared minus 1 itself is the difference of two squares again. So I'm going to factor that. So that's going to give me 2 times x squared plus 1 times x plus 1 times x minus 1 all over x to the third power. So the critical numbers come from two sources, usually. The critical numbers will happen where the derivative is equal to 0. Okay, and normally we would also look for where the derivative is undefined. But we have a special case here, because at a glance we can see that the derivative will be undefined at x equals 0, right, because of this denominator. However, right from the beginning, I pointed out that 0 is not in the domain of the original function. So if you have a value at which the original function is undefined, that can't then be a critical value. It's the original function is already undefined there. So the one value that we might have gotten where the derivative is undefined can't be used. So our only critical numbers are going to come from setting the derivative equal to 0. I should point out we're still going to use this number to make the intervals. We just won't be expecting the graph to exist there. Okay, so when you set a fraction equal to 0, the only way that's going to happen is if the numerator equals 0. So really, I'm doing this. 2 times x plus 1 times x plus 1 times x minus 1. The numerator has to equal 0 for the derivative to equal 0. Dividing both sides by 2, I really can just ignore that 2. So I'm setting each of these factors equal to 0. So x squared plus 1 equals 0, x plus 1 equals 0, x minus 1 equals 0. I'm using the zero product property. Okay, so this first one will give me x squared is equal to -1. This has no real solutions, right? If I took the square root of both sides, it would be imaginary. This has no real solutions. You can't square something and get a negative number. So forget about that. So our critical numbers are going to be x equals -1 and x equals +1. So these are the only critical numbers. So as we make our number line, we will use these critical numbers, and also we will use x equals 0 because the original function is undefined there. So here comes the number line. Because I am going to do the derivative, I'm going to just put an f prime out here to remind me that that's what I'm doing. So let's see, we've got -1 and 0 and +1. So this creates the intervals. We need to pick some test values. In this first interval, I think I will use -2. In this interval, I'm going to use -1/2. In this interval, I will use +1/2. And in this interval, I will use +2. So I need to use this expression for the derivative to do the test. All right, this is the first derivative test. We need to substitute each of the test values into the first derivative and find out if we get a positive value or a negative value. So it pays to be strategic about which version of the derivative you're going to use. And I feel like this version right here is the one that it's going to be the easiest for us to quickly tell if it's positive or negative. All right, I'm imagining if you raise something to the 4th power, that automatically makes it positive, that type of thing. Okay, so this is the version I'm going to use. So let's start with the -2. So we're going to do 2 times -2 to the 4th power minus 1. So I've got 2 times -2 to the 4th power minus 1 divided by -2 to the 3rd power. Okay, so this is going to give us 2 times +16 minus 1 divided by -8. So in the numerator, I'm going to have a positive number, right? 16 minus 1, this is positive. In the denominator, I have a negative number. So a positive divided by a negative is a negative. So I know the derivative is going to be negative in this interval. that tells us that the function itself will be decreasing in this interval. All right, so how about negative 1/2? So I'm going to have 2 times negative 1/2 to the 4th power minus 1 over negative 1/2 to the 3rd power. Okay, well, negative 1/2 to the 4th power is going to be less than 1. Maybe I'll go ahead and show it, but 1/2 to the 4th power is 1/16. So because it's an even power, it's going to be positive. So I'm going to have 1/16 minus 1. Okay, and down here, this is going to be negative 1/8. But look, 1/16 minus 1, that is a negative number. And then a negative number times 2 is still a negative number. So we have a negative divided by a negative, which will give us a positive for the derivative in this interval, which tells us that the function is going to be increasing in this interval. Okay, so for positive 1/2, let's see what changes. So this will be 2 times 1/2 to the 4th power minus 1. Okay, over 1/2 to the 3rd power. So that's going to be 2 times 1/16 minus 1. And this is going to be positive 1/8. All right, 1/16 minus 1 again is a negative number, so the numerator will be negative, but the denominator is now positive. So a negative divided by a positive is a negative, which means that the function will be decreasing in this interval. And finally, we'll do positive 2. So we're going to have 2 times 2 to the 4th power minus 1 over 2 to the 3rd power. So that's going to give us 2 times 16 minus 1 over 8. So that's going to be a positive in the numerator, positive in the denominator. The derivative is positive in this interval. So the function is increasing during this interval. That tells us that we will have a relative minimum at negative 1, and we will have another relative minimum at positive 1. Now, does this tell us that we have a relative maximum at 0? All right, which is what we would normally say. Why is that not the case this time? All right, this is not a relative maximum. Why not? Well, because of this. The function is not defined at 0, so it can't be anything. It's not a relative max, not a relative min. It's an asymptote. Let's go ahead and find the y values so we can have the entire point. So don't forget that the original function is f of x equals x to the 4th power plus 1 divided by x squared. So evaluating that at negative 1, we will have negative 1 to the 4th power plus 1 over negative 1 squared. So that'll give us positive 1 plus 1 over positive 1, which will give us 2 over 1, which obviously is equal to 2. So that means that we have a relative minimum at the point negative 1 comma 2. All right, let's do that again, evaluating at x equals 1. So I think right away you're going to see that nothing actually changes here. Because of the even powers, whether it's positive 1 or negative 1, you're going to get the same exact thing. So that means we have another relative min at 1, 2. Let's take a look at this graphically. So here you see the relative minimum that we predicted at -1, 2, and the other one at 1, 2. Notice that here at x equals 0, we do not have a relative min or a relative max. This is an asymptote, again, because the original function was undefined at that value. That's why it was not a critical value. That's why we don't see like a sharp turn or something.